Okay, welcome also from my side to this conference, or to this section, to this presentation, which will be the so-called solid-state bioprocess inspired valorization option. And as we've heard a lot during the last days, especially on Tuesday and Wednesday, we have one element in the bauxite residue which actually causes a bit of an issue if we talk about valorization, and that's the sodium. I think I've only heard one presentation where the sodium was actually beneficial for valorization, and that was the presentation of Michiel today. That content of sodium is one of the main factors why the bauxite residue is reused in very low amounts. So we have the global reuse of around 3% of the yearly produced mass of the bauxite residue. And also when we look, for instance, at a certain application in, for instance, the construction sector, we see that the amount of bauxite residue which is used is relatively low, of course, logically. And there it sums up to around 1% only. And when we have a look at the examples of in what applications it is used in the construction sector, we can see that it is mainly used in aggregates, or in road bases, or as a feed material for the production of ordinary Portland cement. There we are also additionally limited by the chemistry of the bauxite residue, which deviates too much from the chemistry that we need for the ordinary Portland cement. So actually what we see is we have mainly low added value applications which dominate also in the construction sector. So the volume used in total is relatively low as well. When we have now a look at a higher added value application of the bauxite residue in the construction sector, we could think of a binder material. So what happens if we add just water to the bauxite residue, or an alkaline solution to make an alkali activated material, so the material that Michiel presented just before? Well, we see that it doesn't work. So the material doesn't harden. So if you would build something from that, it will just collapse. And the reason for that is that, in contrast to these cement precursor materials or these alkali activated precursor materials, we do not have hydraulic phases in the bauxite residue, and we don't have a glass that can react with an alkaline solution. So basically, we cannot form a binder material from it. You have just seen before from here the presentation that we try in our group to transform the material into something that can work, which was like in a high temperature process where we first produce a glassy material, which then can be alkali activated material, can be then alkali activated to produce a construction material which has properties which are decent enough, or in case of Michiel, you've seen the properties can be even very high with around 100 megapascal. And this is also a bit what you've also seen yesterday in our short demo of the containers. That's one of our main aims in our research group. We want to propose novel valorization processes where we can use the residue in alternative binders or other monolithic construction materials, where we can maximize the content of bauxite residue. But that means also that the main reactions have to come from the bauxite residue itself, so either from the slurry or from the dried form of the bauxite residue, or as Michiel presented, from a material that we create during one of these valorization processes, for instance, the bauxite residue slag or the glass from the bauxite residue. For us also very important is that we make processes that fit the characteristics of the residue. In case of the residue, that's of course the high alkalinity of the bauxite residue we have. And there I come back basically to the sodium thing. Or the sodium content. For us, it is in any case beneficial to have, because then we can make, in this case, better alkali activated building materials. And for us, it's also important, what is the perspective actually of the alumina producer? Because we, of course, want to not fit or bring the residue just in an established industry. Let's say we don't want to make ordinary Portland cement because we cannot use that much in this industrial sector. No, we want to make processes that the alumina industry theoretically can do themselves. So 2 points are very important. If we need additional materials, they should be either present in the alumina refinery or at least in reach of the refinery, which of course is also a cost factor. And there should be access to infrastructure. So if you want to treat the residue in some way, it is of course beneficial if the alumina industry has either the equipment or has access to the equipment or has the knowledge on how to use that equipment. One example would be, for instance, an autoclave. And that is also what I want to present today. In contrast to Michiel, I will go to low temperature today, where I try to transform the bauxite residue at a low temperature process into monolithic construction materials. And as you've seen in the title of the presentation, we termed it or named it the solid-state bioprocess inspired valorization option. And you can see why now in this slide. When we have a look at the Bayer process, simplistic, we can say we have the bauxite and we add a sodium hydroxide solution. And we put it in an autoclave. It reminds me always of a pressure cooker because we have the high temperature and the high steam, where we in the slurry state have the dissolution of the aluminum hydroxides from the bauxite, which eventually gives us alumina after the processing. And we also have the dissolution of silica-containing minerals in the bauxite residue, which of course make then part of the desilication products and go to the bauxite residue. When we now take a dried version of that bauxite residue, for instance, a filtered residue, we come to the valorization option, which I would like to present now. Because in this valorization option, we used around 90 to 100% bauxite residue and added additives to the residue and mixed them. And these additives could be, for instance, siliceous additives, which could be a clay or sand, or bauxite. And we have seen when we do this and we add an alkaline activator, so again, similar as in the process of Michiel, and we press this material, and we put these pressed samples, these green bodies, in an autoclave in a very similar conditions as in the Bayer process, with one exception. We have a solid state process as we put these bricks inside the autoclave. We see something similar as in the Bayer process. We also see the dissolution of the aluminum hydroxides, which are still left in the bauxite residue or reprecipitated, as we've seen in the presentation before, and the dissolution of silica-containing materials. These can be also now part of the bauxite residue, which could be, for instance, quartz, which is left in the bauxite residue, or which comes from the additives. So, for instance, it could be kaolinite, which is in the bauxite, or in the clay, of course. What we then do is we leave it for a while in this autoclave, and after a certain residence time, we can take the material out of the autoclave, and what we see is that we have a product which is water insoluble. So we basically have a solid brick which does not dissolve in water anymore. We also measured then the compressive strength of these materials, so the mechanical properties, and what we've could see is that we reached properties which are quite decent already, around 17 to 50 megapascal, and we saw a trend basically that if we add more of the additives, so in this example we used up to 10% of siliceous additives, we also have an increase in the mechanical properties. So we see that we need some additions because they are beneficial in increasing the mechanical properties. But we can still see that without any additive, we still reach properties which are around 15 megapascal, which is for some applications already good enough. We then also had a look at the microstructure to see what is actually happening. And we can see here in this micrographs that we actually don't see that much. We see a mix of amorphous phases and finely crystalline phases, which are very well distributed in the matrix here. And we see a relatively dense material, but that's it. We cannot really see much more because the crystals are just too fine, and also the mapping. So an elemental mapping of this sample was very difficult because we have just too fine materials in the bauxite residue. And then we decided to do a mineralogical investigation to see what is happening before and after the autoclaving. So what you can see here is are basically two XRD diagrams or diffractograms of a sample of bauxite residue with 10% of a siliceous additive. And you can see here with the dotted line the situation before the autoclaving. So before we put it under hydrothermal treatment. And with the solid line, you can see what happens after we take it out of the autoclave. And what we can see here is that we have some dissolution of phases. In this case, gibbsite and boehmite from the bauxite residues. So the aluminum hydrates are dissolving. And also we see that there's a dissolution of quartz, which can be now partially from the additive, but it can be also still present in the bauxite residue. And we see at the same time that there is also formation of certain phases after the autoclaving. And in this case, we could detect a zeolite mineral, which was analcime. And you also see that the peaks for concrinite is increasing. So we basically see a transformation from the initial phases to these novel reaction products in the end. We also, so what we cannot see here is what happens, for instance, to the amorphous phase. So in the previous presentation, we have seen also that there can be some amorphous content in the bauxite residue, but we cannot see in XRD really what is happening with the amorphous content. So we did a spectroscopy to see what is the environment or the coordination of certain elements. And we picked aluminium because there we can really see what happens with the phases that we have in the bauxite residue before and after the autoclaving. And here you see again With the dotted line, that's the situation before the autoclaving, and with the solid line, how it looks after autoclaving. What we can see is before the autoclaving is that we have predominantly aluminium in an octahedral configuration, while after the autoclave, we basically have no octahedral coordinated aluminium anymore, while we have only tetrahedral aluminium. And that basically shows us that before the autoclaving, we have phases that contain mainly octahedral aluminium, and they transform into phases that have only tetrahedral aluminium. And that also is in line with the XRD results, what we see, because gibbsite and boehmite and also kaolinite from the clay, for instance, they all have aluminium in octahedral configuration, and it transforms into phases which have aluminium in a tetrahedral configuration, and that are the phases cancrinite, analcime, and what we also can assume here is most likely that we form an amorphous binder phase, similar to what Michiel saw in his samples, because we have all the ingredients to basically make a geopolymer or these alkali activated binder. It is also likely, when we would assume that we still have aluminium hydroxides, which are amorphous, in the bauxite residue, that they transform to something which has a tetrahedral configuration, so takes part of this binder formation in the end. So the key scientific takeaways, I would call them, for this process are that we have actually a similar concept as in the Bayer process, just that we have it in this case in the solid state, because we basically bring the bricks inside the autoclave. And we have certain phases from bauxite residue and the additives that dissolve during that hydrothermal conditions and lead to the formation of new reaction products, which basically form a binder material around the non-reacting phases, which would be, of course, the hematite that does not react in this process. And we can still, although we don't have that much reaction, decent compressive strength. But we have seen also that the more the additives we add, the higher the strength could be. But as mentioned before, there might be some applications where we don't need that high strength. Also, you've seen yesterday that for us, it is always important to think a bit behind or beyond the lab scale, because we don't want that all these processes just stay at an academic level. We want to go a step further, and one step further, or basically the first step further, would be to make a flow sheets to see how could that take place, for instance, in industry or even within an alumina industry. And there we could say we start with the bauxite residue slurry as it leaves the process of the Bayer process of an alumina refinery. We add certain additives to that could be siliceous additives. I mentioned 2 of them. However, we are not limited to these. And of course, it also depends what is available in an alumina plant. So it might be that a lot of additives are suitable for this process to be added. And then we could filter that material, which could be then in a filter press, for instance, to separate the dry cake, which is then the slurry or the bauxite residue and the additives, and the alkaline liquor. The alkaline liquor conventionally goes back to the Bayer process, but we could also think of another route, which I will explain in a minute. If we use, or if we bring the alkaline solution back to the Bayer process, we need an alkali silicate solution. That's also what you've seen in the process of Michiel, to activate basically the solid mix. If we don't bring the alkaline liquor completely back to the Bayer process, we could have a different option. We could reuse that by taking or by adding some alkalis to that and some additional silica, which could be quartz or a sand, which is even impure. And we put this mix in an autoclave, because that's actually a traditional way of making these alkali silicate solutions, which are needed to make these alkali activated materials. So theoretically, that could be also done by adding some components to the alkaline liquor after filtration. After that mixing state, where we then basically mix the solid and the liquid together, we have as a next unit operation the pressing step, where we basically put or bring the material in the shape we want to have. And then we have the hydrothermal curing as the next step, where we basically have the reaction of these pressed bodies to the final products, which can be then tiles, bricks, or anything you can imagine as a construction material, which can be pressed in shape, basically. So the central takeaways of that presentation or this process is that this valorization route can deliver products for civil engineering, like aggregates, bricks, or tiles. But we are not limited to that, because you've seen that we form zeolite minerals, which is a very interesting mineral group. which often is described as an adsorbent of pollutant from wastewater, for instance. So we could also think of a more functional use of these materials. What we've seen also is that in this approach here, we used very high amounts of bauxite residue. And we see that the reactivity and the performance comes partially from the bauxite residue, which would not happen if we would just use an ambient curing, for instance. So we need to go to these conditions, these hydrothermal conditions, to really get the remaining reactive phases from the bauxite residue into reaction. And of course, also the reactivity comes from the additives we add. However, we think that this option has potential to be implemented in-house in an alumina refinery because of the two mentioned reasons already. We have additional materials that work, which are normally available in an alumina plant. So in case of the bauxite, we could even think of a high silica bauxite, because for this process, actually, it would be helpful to have silica and alumina, which can then form that binder material. And we also have autoclaves available in an alumina plant, or at least that knowledge is available, because of course we use here a slightly different autoclave to make these binder materials, which resembles more like the autoclaves for making aerated concrete. However, the knowledge is there, and that makes the alumina producer then of course less dependent on other industries. And we believe that this process can be then a low cost and a low risk application. Of course, there are still remaining questions and also some future work. For instance, we of course need to prove this process in a bigger scale. So the scale up is pending, and the aim is to increase the technological readiness level of this process. And of course, very important for construction materials is also the durability. We have also heard a presentation about the leaching. That's also very important. And there is still a lot of room for optimization of the mix design, for instance. And that could be done, for instance, by a design of experiment approach, which is very interesting to screen all the different additives and so on, and different mix designs. Very important also heard it today in Timmy's presentations is, of course, is it economically feasible, and also what is the environmental aspects of this process. And we were actually lucky because we got the chance to prove it in a bigger scale. Just 2 days ago or 3 days ago, the Everest project was granted for Karl Löwen, where we basically will build a new container. So you've seen already the first 4 or 5 containers, and we want to build a new container which has an autoclave where we can do this hydrothermal curing. So we will be able to demonstrate this technology at a bigger level, and then also prove all the points what we've seen here to check the durability and so on. With that, I want to thank you for your attention, and if you have questions, please ask the questions.